Hi guys, thanks for coming. I'm Peter Neumark, as you just heard, and I work for Prezi. And last week, Prezi invited Professor Philip Zimbardo to come give a lecture in Budapest. Ever since the Stanford prison experiment in the 70s, he's been considered one of the leading minds in psychology. He's also a Prezi user. Another Prezi user is U2 singer Bono, who gave a TED Talk using Prezi. And so is one of the leading candidates in the last presidential primary in South Korea, who also presented with our software. When you have really high-profile users like that, you start to really worry that in the critical moment, that Prezi is really going to load. And you start tossing and turning at night if you're not really sure that's going to happen. So we really want to be sure that everything works out for our presenters. But what actually happens behind the scenes when Zimbardo or any other presenter hits play? First, the client running on their laptop will go to one of our web servers, but most likely this web server won't be able to actually respond just by itself. It's going to have to talk to other servers. And some of these other servers might actually be located in a different data center, quite far away. Now, the focus of my talk is this communication. So we're probably talking about how data centers, how communication goes between servers that belong to one company, but they're in different data centers, and what the most efficient means for that is. Now, generally, when we talk about communication protocols, you want them to be simple to use, of course, because simple is always good. You want them to be efficient, and they should be flexible so they can be changed whenever you need to change them. In reality, pick any two. So they're going to optimize for two of those. Third one's going to be kind of out of luck there. But why are we even talking about this? Like, doesn't everybody use REST and JSON? Put your hand up if you use REST and JSON. Okay. Put your hand up if you don't use REST and JSON. Nobody. Not a single person in the room put their hand up. We have a winner here, like, what's the point, right? It's obvious. REST and JSON is the way to go. And what could be a better endorsement than the fact that Facebook is using REST and JSON for the Graph API, and Google has like a bajillion APIs using REST and JSON. Why use anything else? It's simple, it's flexible, and up until pretty recently, it was about as efficient as you could get with JavaScript, so, that's not too bad. And for a developer, REST and JSON just feels right. Everybody already knows HTTP. JSON syntax, like, that's Python syntax, Ruby syntax, and I could go on and on, it's nothing new. Documentation, that's a list of URLs. That's pretty much it. And you don't need a client library. Curl is your best friend. No porting, no trying to understand what's going on. Just use curl, that's it. So how could it get any better? It's actually very close to perfect. And if I was going to compare this to a razor blade, I would say this is a disposable razor that you buy for 5 cents. Gives you a perfect shave. Never have to read an instructions booklet. You don't even need to find an electrical socket. It just works, and it works really well. So JSON and REST together are a really, really good choice. But sometimes you want that extra bang that you get when you invest the time and the money to buy one of those really high-class electrical shavers. You can improve what you get with REST and JSON, although it already is very good. For example, what if you could factor out these generic protocol details? And what I mean by that is things like compression, right? So you're sending all this data along. We have an API that serves a 30,000 element list every minute. Sorry, every second. What would be the win if we could compress that? It would be huge. It would be gigantic. We can't do that easily because in order to put compression as the protocol, you have to modify every single API and API consumer to allow for that. What about rate limiting? What about encryption? I'm not saying you can't do this. It's just that you have to re-implement this every single time you come up with a new API. Wouldn't it be nice if you could do several wire formats? Like have a JSON wire format if your client is in the browser, and have a binary one if it's a server somewhere and you need to be efficient? Finally, what about RPC semantics? Now, I know a lot of people are not fans of RPC. RPC, by the way, is remote procedure calls. But I am, and I'll show you why. Let's look at what it looks like to get the local time from a distant server using REST and JSON. It's not really difficult. I mean, you just make a request, take the response, you load the JSON from it, and then you interpret that as a timestamp, and you're done. So it's pretty logical. But that time up there, I don't know if you can see the font, is the only thing you really want to know. And everything that's in orange can throw some sort of exception. It usually won't. But when you have 25 million users pounding away at your infrastructure, each one of those orange bits is, every now and then, going to throw an exception. So you're going to have to do something about that. Now, the server part of it, it's a lot safer, but there's a lot of noise in there. So that datetime.now, that's the only thing you really want to return. But then you have to make that into a string, and then you have to put that in a dictionary, and then you have to serialize that dictionary into JSON, and then you have to create a response and send it along. Now, this is, on the one hand, really good, because you have perfect control over that response. You need to set headers, you can set headers. You need to set the response code, you can set the response code. There's no fancy framework getting in the way. You know, it's just you and your HTTP response. Nobody can come between you. But there's no way to generalize over that. You have to do everything by yourself. What does this look like if you have a remote procedure call? Wait for it. This is the client. Bam. Get time. That's it. Probably won't need to give it a server so it knows where to go to. That's all. Yes, it can throw an exception, but that's all you have to do in your code. What about the server part? It's probably just going to be returning that value. That's pretty much all you have to do. All the plumbing of making a byte stream out of the data, then putting that into a request, sending that request along, unpacking it, all of that, that can be abstracted away if you use RPC. So I do like RPC. I'm not saying REST is wrong, but RPC is pretty cool, and it's tough to do with JSON. Tough to do well. But let's stop talking about a wish list of things that would be kind of nice to tack on, and let's look at what is already out there and what you can do with REST and JSON and with all these other things and kind of how that fits together. I'm going to start off by talking about encoding efficiency. This is one of those magical terms. As soon as you see it, people start yawning, like, oh yeah, who cares about encoding efficiency, right? We have a limited bandwidth. It doesn't matter. Actually, this is one of the coolest geeky subjects I have ever had the honor of kind of digging into, and I highly recommend this field of study. For the purposes of this talk, I'm going to use an example I found on Wikipedia. It's a very dumb, stupid protocol. It's the foo question protocol. You can ask questions with it. You can make messages that have two parts. One part is the actual question. For example, anybody there? Another part is a tracking number that you give to each question so you can keep track of which answer the question is for, which question the answer is for. So this guy's already thinking about buying that girl a drink and incrementing the tracking number on that question, the next one. So how would you classify these wire formats? You can say you got text wire formats and binary wire formats, and that's all well and good. There's also another thing you can use to classify them. You can say you have the static wire formats, where you need some sort of agreement on the structure of your messages before you can start communicating. And then you have the dynamic ones, where that's just not necessary. I'm going to start with the part that everybody's familiar with. You have the dynamic text-based protocols like YAML, JSON, XML. This is the stuff we generally use. It doesn't require any explanation. What about XML? What about static text-based protocols? You could say XML plus some sort of schema would fit this in a way. So I have a schema up there for this foo question element that allows me to validate this element. But if I was really strict, and I knew that both the sender and the receiver had this schema, I really wouldn't need to put any elements in my XML. I already know that the first element is going to be a tracking number, it's going to be an ID, second number is going to be a string, second thing is going to be a string, it's going to be a question. So XML is a bit conservative, it's a bit redundant. If we knew both of them had a schema, we wouldn't really need that. Okay, now let's look at the binary version. There's a dynamic binary protocol called ASN1. It's one of those old school technologies that never dies. It was invented sometime in the early 80s. You can find it in radio telescopes, satellite links. It's in your open SSL certificates. Everywhere you look, there's like some sort of ASN1 under the hood. And it's lived for so long because it actually works quite well. Very simple. Before you encode any value, you say what kind of value you're encoding and what the length of it is. So you say an integer is coming up, its length is 1 byte, and then you say number 5, the tracking number, right? So you have a lot of type information in the message. It's still a lot more efficient than any of the text-based formats, but there's a lot of explanation as to what this data is. Now let's look at the exact opposite. Okay, this is a static binary protocol called the C-BLAT. What a great name, BLAT. Anybody use C in here? Ever? You guys are lucky. Wow, okay. Times are changing. Okay, so anybody who's ever looked at C code, you've probably seen this trick where if you tell the compiler that a structure is packed, then it will put all the fields of the structure right after each other. And so you can just take that continuous block of memory, copy it to a file or another place in memory, and you have a new structure. And then you can load it from a file. It's kind of a hacky thing to do, but people do it all the time nonetheless. This is the exact opposite of ASM1 in the sense that there is no metadata. So you just take that memory. You don't know where one value starts, where the next ends. You just write it as a set of bytes, and you hope that the person reading this had the same notion of what that byte stream should be. If you use the same program to read it, and you have the same compiler, and you're using the same architecture, and you're lucky, then it works out. But like I said, this is actually used in production systems to this very day. Now let's look at another static binary protocol that requires a little bit less luck to actually work. This is Google Protocol Buffers. So we have a message definition that has 2 fields. Can you guys in the back see it? Cool, all right. And then you see the message, the byte stream itself. Now, you might notice that there's a little bit less data here than we had in the ASN1 version. Of course, there's a little more than just the data itself. Google Protocol Buffers tried to find this sort of compromise between ASN1, where everything about the data is in the message, and the C-BLATs, which have nothing. It's just the data itself. And so what it does is before it writes a field's value out into the byte stream, it writes a tag which says field number 1 coming right up. And then once it's written that out, it writes the value of field 1. Then the same thing for all the following values. So in this case, you see an 08 up there. That means the next byte is going to be field number 1. And then you see the value 5, which is the tracking number. Same thing for that 12, which is actually an 18 because this is in hexadecimal. That represents the fact that field number 2 is coming up in the byte stream. Okay? Why is this better, or how is this significantly different than ASN1? We're not really talking about what types of data are coming along. We're talking about what field it is. If you look at the message definition, you see an =1 after tracking number, and you see an =2 after question. What that means is I'm assigning this field number to that field. And if you see that tag in the byte stream, that means that's the tag that's coming up. In a way, this is actually even more information than what you have in ASN1. Because in ASN1, you said, here's an integer coming up. The next 4 bytes or whatever are going to be this integer. Here you're saying, when you make an object out of this thing in Python, set the following value to be equal to the tracking number property of that object. But because you have this, you don't really need to record any type of information. That's already in the message definition. Now, actually, the guys at Google did cheat a little bit. So this tag ID reserves 3 bits for the field type. I actually don't know why they put that in there. You don't really need that because that's in the message definition. But they have that, and the remaining bytes are there for the field ID. And this tag can be 1 to 4 bytes. So they have this very clever encoding scheme where they use only as many bytes as they need. Let's see how they stack up in terms of bytes. Okay, so the raw data is around 15 bytes. That's the absolute bottom you can do without any compression. Protobuf is pretty close. Then you have ASN1, which is dynamic, but it's not far behind. Then you have the stuff we usually use, YAML, JSON, pretty close. And then you have XML, which is enterprise. So it's still dynamic text like the other two, but it's twice as fat because it's enterprise stuff. And finally, you have the CBLAT, which is the largest, but only because I chose an IVE implementation. It would be really easy, actually, to make the CBLAT the smallest. But that would mean the code would be slightly more complicated. Okay, but efficiency isn't the only thing that's important about a protocol. And you guys can stop yawning now if you're not into this geekery. And let's look at what a flexible wire format is. So if you want to change your wire format, if you want to change your messages as you go along, how easy it is to do that. If you have a dynamic message format, then you just start sending different messages, and you hope and pray that they'll understand. And that's pretty much it. But remember, for static messages, you have to have some sort of agreement on what the structure of the message is. And so if you're starting to send different messages, you're kind of breaking up that agreement. Now, different formats are more or less permissible about that. The CBLAT system is very simple. You can extend messages. So extending messages would be to add a field to foo question, which would say what the language is. You can't change fields. So if you want to change the tracking number from an integer to, say, a string, you can't do that. And you can't leave any fields out. So if you leave out the tracking number, things are going to go bad. And that's because it's tied to the memory representation of this structure. What about XML and the schemas? This is an interesting case where the message doesn't really include anything about the message, but it just references a schema. So anytime you have a valid XML with a schema, it's going to say, hey, if you want to verify that I'm correct, go to this URL where you can find my schema, and then you can check whether I'm OK or not. And so if you just start changing the format, you start referencing a different schema in the message, and you're done. That's all you need to do. So you can do anything with XML. That's why it's so bloated. What about protocol buffers? You can extend messages. You just take a new field, gets a new field ID. That's absolutely fine. You can't really change fields. You can probably do that because there's those 3 bits in the tag that would maybe allow you to do that. I highly encourage you to stay away from that stuff. Don't ever change any fields. And omitting fields, you can do that as long as they're optional fields. So I just extended the foo question protocol with a string. That's a language. It gets the field ID 3. And as you can see, it starts with optional instead of required. Now, a lot of times, I think it doesn't make sense to use required fields. Instead, some people at Google say, don't ever use anything but optional fields, because the required fields are just going to bite you. Now, what happens when there's a mismatch between the version of the client and the server? So I, as a client, am sending a message or a field, in this case language, that the server doesn't understand. If it's an optional message, they're just going to throw it away. Don't understand, whatever. Similarly, if They send, or if they omit something, which is an optional field, I won't care. So it's very backward compatible, actually. It works very well in practice. What about simplicity? This is the ultimate test. Could your 12-year-old nephew figure out how to use it? That's basically what simplicity boils down to. JSON is simple. Hell, your 8-year-old nephew could figure out how to use that thing. XML, also fairly simple. When you add schemas, things start to get complex. And ASM1, because it's old school technology from like 30 years ago, yes, it's going to be tough to use. What about protocol buffers? I'd say it strikes up a pretty good compromise. Here's how to write a stream, how to write a message to a stream in Python. So you import this foo question object, you set properties on that object, and then you call the object's serialized toString method. And that's that. It's not too bad. What about writing, or reading a stream, sorry? Same thing. You import the type, you call parse from string, you give it a stream, and you're done. The big question is, in that line, from foo question pb2, import foo question, what's that foo question pb2 module? Where does that come from? This is where the Proto-C compiler comes in. So you have a protocol definition, like that message foo question we saw earlier. You use the Proto-C compiler to create a Python script, which is generated code that you can then call serialize to string on or parse from string on from your application code. So it's actually very convenient to use, but you do have to modify your build chain to do that. Okay, and then stepping on from protocol, Google Protobuf, let's look at Apache Thrift. Now the story here is that despite using REST and JSON for all their front-end services, Google decided, hey, we need something much more efficient for in-house stuff, so they wrote protocol buffers. And then some guys, probably for better stock options, decided to go to Facebook, and they're really, really missing that. So they created their own implementation called Apache Thrift, which does the same thing, except it adds RPC semantics, you can have exceptions, you can have collection types in your message definitions, you can have constants, and it supports 20 languages. Protocol buffers supports 3. So it's a pretty good package. It's a significant upgrade, I would say. And I think RPC, of all the things I listed, is the biggest change. So if we were using Thrift instead of protocol buffers, how would our message definition or how would our protocol definition look? So you have this struct at the top. That's the same thing as message in protobuf. It has 2 fields, an integer and a string. No surprises here. What about the other 2 parts? Let's start with the bottom. Service, foo service. So remember how I said in RPC you have these methods you can call remotely? In Thrift, you have a service which has service methods. These service methods can use all the types you define as input and output. So in this case, we have an ask method which receives a foo question, and it can throw an exception. If the remote server doesn't know the answer, it just raises a I don't know exception. And then you get that back. If all goes well, it just returns a string. Now, this is very different from OO. So the structs and the exceptions have only data. The services have only methods. And there is only data going through the wire. There is no fat object. Like, I don't know if you've ever heard of Corba. Very scary stuff. There you have like these big fat objects kind of chugging along the wire like really slowly. This is very different. Only data going across the wire. So this is how you'd use it. You'd say fooservice.client, you initialize it, and then you say ask. And you give it a foo question, and that's that. Pretty simple. The interesting part here, actually, is what you're giving to the constructor of that client object. You're giving it a protocol. Why would you need to do that? We didn't see anything like that with protocol buffers. Why do you need to have any kind of protocol? So the protocol is what turns an object into a byte stream. And Thrift has like 4 or 5 of these, but you can always write your own. It's actually really simple to do. So Thrift supports binary formats of several kinds, and JSON by having different protocols implemented in different languages. And it's really simple to do. If I just change that to tJSON protocol, everything would work, but then I could use it from the browser easily. And finally, we give that protocol a transport, which takes the byte stream and moves it across the network somehow, or writes it to a file, or copies it into a memory buffer, whatever. Now, I have to admit, I really like Thrift. You probably already guessed this by this point. I think Thrift is the electric razor that is sometimes a bit difficult to get started with, but once you use it, it gives you a better shave, and it's definitely worth the investment. But we figured we don't really want an electric razor. We want a robotic barber that you just sit down and gives you a shave without you doing anything. So we created this thing called Thriftify. It's basically a bunch of utilities kind of tacked onto Thrift, so it's easier for us to use. I want to share some of the cool things we did with Thriftify. One of the early problems we had is we have a lot of Python applications that use Django, but it's not so easy to have a HTTP Thrift server working through Django. So we added that. In your URL patterns, you just add another include, and then the implementation of the server side of this ask function would be those two lines. It's just a return. There's nothing special going on here. We automatically generate thrift services for the CRUD methods of models. So let's say you have a Django model called profile. For active record, I think this would be very, very similar. In fact, you could do this just based on a raw SQL table. You have a username, an age, and an is@RuPy field. Based on this, Thriftify can give you a thrift definition that includes a profile row structure, and it will give you a service that has methods, read, update, delete, for interacting with the database. Now, one thing that's really cool about Thrift is if you see, it says service profile CRUDs extends base. You can stack services on top of each other. So not only does this profile CRUD service have a read method, it also has a bunch of other methods that you can use on any Thriftify endpoint. What are these methods? Well, one is the info method. The info method is great because one of the things I really hate about static protocols, even though I generally like them, is the fact that you have to somehow find the definition for your protocol. So let's say I already know the IP and the port that I want to talk to, or the URL or whatever. That's not enough. You have to find that agreement about what a messages structure looks like. Now, in Thrift terms, that's, of course, the Thrift file. So instead of trying to hunt down the Thrift file or emailing the guy who wrote the service saying, send me your Thrift files, you can actually just talk to the endpoint. You can send an info request, and it will give you back all the Thrift files needed to generate the code so you can talk to it. So any Thriftify service, as long as this feature is not actively disabled, you can go to, get the Thrift definition, load the generated code based on that Thrift file, and talk to it. Thriftify is a very smart URL scheme, I think. It accepts something like JSON plus HTTP something and turns it into HTTP something / ask / JSON. So it puts the method being called, the service method, and the protocol at the end. So you already know which protocol you're going to be speaking about. You already know which method was called. If you call the info from between servers, it would be info / binary. Why is this good? It's good because you can use all sorts of load balancer magic. You can say, this is a really risky function. I don't know if I want to be running this on the same node where the database is running. I'm going to route that to a different server, maybe in a different data center. From the outside, it looks like one API. But if the risky function ends up pulling the whole node down, I'm still OK. I can still do the read operation, for example. We have op IDs. And this is not something that's Thrift specific. There are other ways to do this, but we threw it in there, and boy, am I glad we did. The thing is, most complex service-oriented companies today have a situation where an incoming request from a client goes through several different internal services by the time you have enough information to respond to the original request. So one request coming from the outside spawns dozens of requests in-house. It's difficult to find out where the bottlenecks are. If something goes wrong, it's not always easy to debug. Each HTTP request that Thriftify sends out has an op ID header, and anytime the server implementation of this RPC method logs something, it logs this ID. So if you just match up the IDs in the logs, you can take a look at the whole request as it came from the outside and know everything about what happened to answer that request. And this is the last one, remote exceptions. So we already saw that you can define exceptions in Thrift, but what if you have an exception that really is an exception? These exceptional exceptions get wrapped in a remote exception message that includes a stack trace, the host name, the HTTP request, the Thrift arguments sent to the remote function, just about anything that could be useful in debugging it. And when you have that, you can much more easily determine what went wrong and fix it up. You can disable this if you have a public Thrift API, but I think this is very useful for in-house stuff. So what does come after REST? For us, at least for in-house traffic, what comes after REST is Thrift and Thriftify. And I'm hoping that once we open source this stuff this Christmas, it will be what comes after REST for in-house traffic for you as well. Thank you. That's all. Any questions? Has anybody tried protocol buffers or Thrift, by the way? Okay, like 4 people. It's good stuff. I highly recommend you try, especially once you have this stuff to make it even easier from Python. I have a question there.
So with Thrift, you also have a compiler like with Protobuf, where you define your message, compile it to the language you want, and
yes.
So it basically works like Protobuf, but has exceptions and a remote procedure invocation.
Yes. Okay. You can do just about anything you can do with Protobuf, but it supports more things.
So, but the workflow is the same, like Protobuf?
Yes.
Okay.
If there are no more questions, then thank you.
Thank you.